Yes, yes.
Okay, sir. So, thank you so much for joining. Today, we'll be solving week 2 doubts and problems related to concept discussed in week 2. My name is Shreya. I'm one of the TAs for this course on regression analysis, and I welcome you to this discussion session. So, before I proceed to anything, is there anything you would like to clear your doubts on, or you know, any other doubt if you have? Because these sessions are primarily targeted for doubt clearance and problem solving. So, if you have anything so far, please let me know.
Yeah, I actually recently joined this course and I was
Okay,
not part of the previous doubt sessions.
all right.
So I would just like to know if anything related to like final exam procedure and anything was said in the previous session.
Uh, I can speak for myself. I did not say anything related to the final exams. Anyway,
Okay.
whatever I say or anybody says, it's better you check it with the NPTEL official team. They will send all the necessary instructions via mail and also in the course web portal.
Okay.
So keep checking that, and in case you have any issues, just post your questions in the discussion forum. I hope you know where you can post it, the link to that discussion forum.
Okay.
Yeah, so just keep a tab on that, and if further question and doubts you need to ask, then I would suggest you to put a mail to the NPTEL team, and they'll be able to guide you better.
Sure,
All
sure.
right. So, with respect to the content and academic content, we'll be able to help you out. So, in that aspect, if you have anything, please let me know. Or if you want a brief overview of what happened in the last week, that also I can share.
Okay, I will go through that through the shared videos.
All right, fine. So, I hope you have seen week 2 lectures, or uh, not.
Yes, yes, I have gone through them.
You've gone through week 2 lectures. Okay. So, can you please tell me briefly what was discussed in week 1 and week 2? Very briefly. You don't need to tell me everything and anything, just like bullet points.
During week one, like we discussed about how to estimate the parameters like beta naught and beta one, and
Yeah.
what are their properties. And during week two, basically we discussed more about the coefficient of determinations and how to estimate the range of these parameters.
Yeah, exactly. So, in week 1, we learnt about simple linear regression. Was it simple? Number one question is, why is it simple?
Yeah, because we considered one single variable and we also
Yes,
considered the linear regressions.
because we considered one single predictor. Okay, and linear, why is it linear? Because it is linear in terms of parameters. So what I want to ask or tell you is that if I have something like this, y equal to beta naught plus beta 1 x plus epsilon, if this is my model, I have another model, let's say this one, y equal to beta naught plus beta 1 x square plus epsilon, and I have another model y equal to gamma naught square plus gamma 1 square x plus epsilon. So which of the three, or one or more, which ones are linear regressions? Can you please tell me?
Yeah, the first one is the linear, and second one is having the quadratic form, so that is not linear.
No, this is also linear, but the variable has
Second
linear
model.
in terms, yeah, second one only. That is also one thing I want to clarify. Second one
Okay.
is also linear because it's linear in terms of the parameters beta 1 and beta naught and beta 1. Okay, but this one is not linear in terms of gamma naught square and gamma, in terms of gamma naught and gamma 1. They are quadratic in terms of parameters. Okay, so this also, if you get something like this where you have something x square, you can always model it as some other variable z and apply the same concepts, same formulas, okay, and go ahead with a linear regression. But here you cannot do so because the estimation techniques and all the formulas are going to change. Okay, this is a linear regression but quadratic in terms of the variable or predictor. So is it clear why we know why it is simple? Because one predictor. Linear because linear is always, just keep in mind, in terms of parameter. Okay, so right, we learned about simple linear regression. We learned about visualization. The easiest visualization is what? It's a scatter plot. So you would have x over here and y over here. Given both are continuous variables, you would have something like this. So this is what you called as a scatter plot. Okay, why is it helpful? Because it helps you to, it gives you a first glance of the data and tells you whether the line that you're fitting, how accurate it will be. Okay, so if you have some quadratic or cubic terms, or let's say if you have a scatter plot something like this, okay, so maybe a linear if you have beta naught plus beta 1 x, then this may not fit your problem well. But if you have something in terms of x square, then maybe you can fit a parabola and so on and so forth. So for visualization purposes, we plot a scatter plot which shows you how two variables, the predictor and the response, y is the response and x is the predictor. So it will tell you how the response and predictors are related. And then we proceeded to parameterize this equation. So we had beta naught plus beta 1 x plus epsilon. So do you remember the assumptions of this linear model? Mr. Rakesh? Okay, so we assumed that this expectation of epsilon is 0, variance of epsilon is sigma square, and also we assumed that x's are not random, and for the purpose of testing we assumed that these variables are normally distributed. Okay, these were the assumptions that we proceeded with. And also after that, what did we do? We went ahead and calculated beta naught hat, beta 1 hat. So this was basically estimation from the data, and then we tested out a few hypotheses. What were the hypotheses? Whether the true beta naught value, the true intercept is 0 or not, or whether the true slope is 0 or not, and so on and so forth. Okay, these everything we discussed, and also we discussed some properties of these estimation parameters, that beta naught hat, beta 1 hat, they are unbiased. What do I mean by unbiased? It means expectation of beta naught hat equal to beta naught and expectation of beta 1 hat equal to beta 1. Okay, and also prior to hypothesis testing, what did we do? We also derived what would be the distribution of beta naught hat and beta 1 hat. So beta naught hat would follow a normal distribution with beta naught, and this one, the variance would be, it would be how much? It would be sigma square 1 by n plus x bar square by sxx, and this one will be beta 1 hat would follow a normal variable, and this would be beta 1 sigma square by sxx. Okay, so these things we learnt, and then we tested these hypotheses whether the true beta naught is 0 or not, and whether true beta 1 is equal to 0 or not. Okay, so this is what was done in the, and we also estimated these when sigma square was unknown. Okay, so now in week 2, what we are going, as you rightly pointed out, so in week 2, what we learned was that we learned more on the coefficient, sorry, where is it? We learned more about the coefficient of determination. So what was it exactly? What did it measure?
It's like measure of how much variance is explained by the model.
Yes. So if you remember, we had divided the total variation in the data set as SST into two components, SS due to regression and SS due to residuals. Okay, where SST is what? SST is variance in the data set. So that is what? That is actually variance in y. So this is I equal to 1 to n yi minus y bar whole square. And of course we would have a 1 by n, but since 1 by n is there in all the terms, we are not going to consider this one. Okay, so this is actually this amounts to the total variation in response. What we are doing, if with the help of this model y equal to beta 1 x plus epsilon, this is the part which is taking care of the sum of squares due to regression, and this is the part which is going to take care of sum of squares due to residuals. So some SS regression was how much? This one was summation I equal to 1 to n yi hat minus y bar whole square. How much of the predicted value? This is this describes actually regression sum of squares. Okay, and this one summation I equal to 1 to n yi minus yi hat, this is the residuals. So yi hat is the predicted value and yi is the observed value. So whatever is unexplained, that part is the residual. So this is sum of squares due to residuals. Alright, so if graphically we have to say, this is my scatter plot and this is my line. So then these vertical distances are actually the terms is this term actually, because here on the line what we have is yi hat, and here where the actual data point was observed, let me draw in a different color. So this one is actually yi prime, and this one was yi observed. So this vertical distance is what we are capturing over here via the residuals, and this is the residual sum of squares. Okay, and one more thing also we learned is that the degrees of freedoms are additive. So here SST has a degree of freedom of how much? It had a degree of freedom n minus 1. Now regardless of simple linear regression or multiple linear regression, the total variation in the data set will always have a degrees of freedom n minus 1. And why so? Because we have this constraint that 1 by n y summation yi equal to y bar. So if you know y bar, and also if you know n minus 1 yi's, you would be able to calculate the nth yi. So if for these n plus 1 terms, it is sufficient, if y bar is known, it is sufficient we know that n minus, we can choose, rather we should say it like this, we can choose the n minus 1 y terms independently. The nth term would depend on y bar because of this constraint in the data set. So SST will always have a degrees of freedom that would be n minus 1. Okay, and for a simple linear regression, SS regression was 1 and SS residuals is actually n minus 2. And how does this 2 come? This 2 comes because we have two unknown parameters in the data set. So let's say this is something beta naught plus beta 1x plus beta 2 z plus epsilon. So this then becomes a multiple linear regression. Okay, at that point also we'll check later if the SST can be decomposed into two orthogonal sections. This is SS due to regression and this would be SS due to residuals. This would be n minus 1 always. SS due to residuals would be how much? It would be n minus number of parameters estimated, number of parameters. Okay, this thing should be very clear, number of parameters and not variables. I should say unknown parameters. Okay, so in this context we would have SS residuals as n minus 3 and then SS regression df would be 2. Okay, but we'll come to this scenario a little later, but this is how the degrees of freedom is decomposed across the sum of squares due to residual, sum of squares due to regression, which and then it amounts to the total SSY. Alright, okay, so now that we are through with that, we also learned something about an ANOVA table. Okay, so what does this ANOVA table show? It gives you all at once what is this, how these all matrix are divided and what is the sum of squares due to residual, sum of squares due to regression, and everything all at once in a summarized form. What I mean to say is that it gives everything in a summarized form. So how does it look like? It looks somewhat like this. So on one column you will have sources of variation. Okay, then this would be regression, this would be error, and then we would have something total. Okay, and then here you would have the next column would be the sum of squares. Okay, so here you would have sum of squares due to regression and here you would have sum of squares due to residuals. Alright, so this one will essentially be, and this one would be SST minus beta 1 hat SXY. Okay, the next column would be degrees of freedom. So for a simple linear regression, this df would be 1, this df would be n minus 2, and total df would be n minus 1. Okay, and this is SST. And then we would have something like mean square. Okay, so MSR or MS regression would be SS regression divided by DF regression. Sorry, DF, not regression. Yeah, this would be DF regression, sorry. And MS residuals would be SS due to residuals by df of the residuals. Okay, and another thing that we are going to check is the significance of the entire regression. That would be tested by an F statistic, and that would also be reported in the ANOVA table, and it would be actually MS regression by MS residual, this term by this term. Alright, is this clear to you? And the degrees of freedom of that F statistic would be degrees of freedom of the regression, and the first n1 would be this one, so it would be an F1 and n minus 2. Okay, so if somebody asks you to check whether the regression itself is significant or not, then the corresponding H0 becomes beta naught equal to beta 1 equal to 0. And at that moment, what you would have to do is that you would have to check this F statistic, okay, the observed value of the F statistic, and then compare it with the F1 n minus 2 alpha by 2 point. So I'm going to come to this one. So you have to say if F observed is greater than this thing, then you reject H0 and conclude that the regression itself is significant. Alright, so I would tell you something a little more about this F statistic and how you can get those cutoff points. So the tables would be provided, or these cutoffs would already be provided to you during the exam, and you would just have to see whether this your F observed from the ANOVA table is exceeding your cutoff or not. And whenever I am writing some distribution alpha by 2 or something, so let's say I am writing T alpha or T alpha by 2, some let's say n, this is the degrees of freedom, let's say if n1, n2, alpha by 2, what I mean is that these points are actually, so T distribution is a symmetric distribution, but F distribution is not a symmetric distribution. Okay, so what I mean to say when I'm writing this alpha by 2 like this is that this is actually the upper alpha point. What do I mean by an upper alpha point? It means that this point, okay, this point corresponds to somewhere here, such that, so maybe this is T alpha n, such that the area above this point is alpha. Okay, similarly, maybe this point over here, this is actually T alpha by 2n, which means that the area above this point is actually alpha by 2. Okay, for F distribution also, Fn1 n2 alpha by 2 means maybe this is the point such that this area above this point is actually alpha by 2. Another important thing I want you to note is that T is a symmetric distribution, but F is not. So let's say you have been given a hypothesis. Okay, let's say you have a hypothesis where your rejection area is your rejection rule is such. Let's say case 1, your rejection rule is that you reject H naught if your T observed is less than some T n minus Tn alpha by 2. Okay, or let's say I'll put a value here, 0.05. Okay, and in the examination you have been given T n 0.05 value. So what does this mean? Since T distribution is actually symmetric about 0, if you are given this point as something, let's say this is equal to 2.35, then you can write this as, so then exactly if this is your 2.35 point, then this minus 2.35, if the area about this thing is 0.05, this is an arbitrary number, don't consider it as the ground truth. Okay, this is just an arbitrary number. So if you have something like this, if it says that this is the point above which 0.05 is the area, then minus 2.35 will be that point below which the area would be 0.05. So in case of a T distribution, it is very easy that way because it is symmetric. T distribution will be symmetric about 0. Okay, but this will not happen for an F distribution. Alright, so for an F distribution, let's say if this is how your F distribution is looking like, if this is the point, if n1 n2 1 minus fn1 n2 alpha by 2, let's say, such that this area is 0.05, maybe this is the point where you would have fn1 n2 1 minus alpha by 2. What it means is that the area above this point is 1 minus alpha by 2, or in other words, area below this point is 1 minus alpha by 2. So if you have to reject something based on whether it falls here or here, you would have to get these cutoffs accordingly from the table if it is not provided to you already. Alright, so just be, I'm just cautioning you and telling you to be mindful of these, because these seem like small things, but these are really important ones. Okay, so if you do not have these provided to you, or if you can't make it out from the table, then you should get in touch and ask for clarifications. Alright, but if for a T distribution, if one end is given to you, you can always go ahead to determine what the other end would be like. Okay, so this was another aspect that I wanted to discuss. and then we checked. So what did we do so far? We took one predictor and wanted to see how it was affecting the response. We fit a model, we fit a linear regression model, we obtained the estimates, and then we checked is the regression itself significant or not. Okay, and then we also got an overview of the variation explained by the model, SS regression and SS residuals, and also we got how we can estimate the proportion of variance explained. So that is essentially your R square value, which gives you whether it will provide you with an understanding of whether the predictor is um, able, very crudely, whether the predictor is able to capture variation in the response. Alright, so after this, what did we do? We proceeded to something called interval estimation. So this was another major focus, that is interval estimation. Now, why do you think interval estimation is necessary? Anybody? So what is actually done in interval estimation? What is the sort of uh, motivation? The motivation is to provide, so in terms of point estimation, whatever we did so far, getting the beta 1 values and beta naught values, these were essentially point estimates. So previously whatever we did, okay, this beta naught hat and beta 1 hat, these were giving us point estimates, and it did not come with a certain level of confidence. Like we couldn't, if we wanted to say that okay, beta naught will be this value, I'm 90% confident that beta naught will take on this value, or I'm 90% confident beta 1 will take on this value. It's not so. It's an estimate, and we don't have any confidence associated. Whereas for interval estimation, what we want to say is that we want to give, the motivation is to provide a range. Okay, with some confidence, or in terms of probability. So what the thing is, what we want to do here is that your beta naught and beta 1, these are your population parameters, and these are unknowns. Okay, we want to tell that I am, let's say I am 90% confident that true beta will fall within some lower bound and some upper bound. Okay, so this one is actually giving me a range where the true unknown population can lie. Okay, if I go back to the example of, let's say, house, like price of a house, and let's say it depends on floor area, beta 1 plus beta naught, beta 1 floor area plus epsilon. Let's say this is my model. Okay, so given a certain floor area, if it is provided to me, and or let's say I have certain data, I can say that this true beta 1, the effect of floor on the price would actually be, there are two ways to say it. I can say that this effect would be something around 0.3, or I could say that I am 90% confident that this effect of floor area would not exceed, would lie between 0.2 to 0.3. So this is what the interpretation would look like. Okay, and now how do we, find this thing? So there are multiple methods to build, and for this also we need some data and distributional assumption. So when we were estimating betas, we did not need any distributional assumption. What did we do? We wrote the model, we wrote the sum of squares due to error, then we differentiated with respect to the beta naught and beta 1. We got two normal equations, solved them simultaneously, and then we obtained beta naught hat and beta 1 hat. Okay, we did not need any distributional assumption, but for testing we needed a distributional assumption. Similarly, for getting an estimate of the getting the confidence intervals, we also would have to get the distributional assumptions correct in place. Okay, so what essentially we are doing is that we are providing this thing, the probability that true beta will fall within, let's say, some z1 and z2, and with some probability which is 1 minus alpha. Then what do we say? We say that z2 z1 is the one minus alpha percent confidence interval for beta. Okay, so this is something what we learned. We'll solve a few problems on this and then our doubts will get cleared. And apart from that, what did we do in week 2? We also extended to a multivariate setup. Okay, so what did we do and why did we do it? Now see, maybe if I go back to this price and area example. So my response is, let's say, price of a house. So it might depend on floor area, but there are several other factors which could be responsible for determining the price of a house. For example, let's say location, very very crucial, and then something else also, maybe whether it is an old or renovated one or a newly purchased one, or let's say some other things, uh, convenience, one storied or two storied, something like this. Okay, so when we are doing this beta naught plus beta 1 x plus epsilon, we are capturing a small part of variance by this thing. So always remember SST equal to SS regression plus SS due to residuals. Okay, so all of these unexplained this SS regression, whichever is explained by only the floor area, and rest any other confounders could go is actually expressing or explaining the sum of squares due to residuals. Okay, now if we want to explain more variation, we need to incorporate these variables into our model. Okay, so it is not always a very good idea to explain to take one variable and expect that it will explain majority of the variation in y. Okay, the variation depends on several other factors, which also we should incorporate to reduce our error in prediction, and that is why we need this multivariate setup. Okay, so what we do essentially in this multivariate setup is this: we model, our model then becomes something like this: y equal to x beta plus epsilon. Okay, so y is nothing but an n cross 1 vector. Okay, x is an n cross p matrix, beta is a p cross 1 vector, and epsilon is also an n cross 1 vector. Okay, in case of a simple linear regression, we would have p equal to 2, and for a multiple linear regression, we would have p greater than 2. Okay, so this is actually a generalized form. Alright, because when we put p equal to 2, what do we have? How does y? So y is the response on, let's say, n number of individuals. Okay, so this would be y1, y2, yn. This is the response. Okay, and here x would be, if the first column is an intercept, everything would be 1, and then we have, let's say, x1, one variable, so x11, x12, x13, x1n. Okay, and then we have beta naught, beta 1 plus epsilon 1, epsilon 2, and epsilon n. So this is exactly how a simple linear regression would look like. Okay, so here if you do it, y1 will be beta naught plus beta 1 x11 plus epsilon 1, y2 equal to beta naught plus beta 1 x11 plus epsilon 2. Okay, so this is a generalized form. Now if we want to incorporate several other parameters, the only thing that we need to change in the model is that we have to add parameters here and insert columns here. Okay, so let's say if I incorporate all these factors, how many did we find? Location, old, new, convenience, 1, 2 storage, or let's say number of rooms. All of these factors, if we incorporate, then a multiple linear regression would look like this. The same thing, y equal to x beta plus epsilon. Model is something like this: y1, y2, yn. Okay, this is a vector. We would have something like this. This would be the intercept: x11, x12, x13, x1n. Let's say this corresponds to floor area. Okay, the next variable that we want is location. Let's say prime or non-prime. It would be a dummy variable, but we'll come to these later on. For the time being, let me write it like this: x21, x22, x23 to x2n. Let's say this is location. Let's say this is number of rooms. 1 BHK, 2 BHK, 1 RK. So this would be x31, x32, x33 to x3n and so on. Okay, number of variables we add, we have to keep adding on to these columns, and we have to extend betas as well. So this would be beta naught, then we have beta 1, then we have beta 2, and then finally we have beta 3, and then if anything else is, we keep on adding, so we'll add it over here, and finally we would have the vector of epsilons. Okay, so then this is how the multiple linear regression is going to look like. Okay, where this n would be the number of entities, individuals, or in this case let's say houses. Alright, and then how will we determine this? So sum of squares due to errors would be none other than, let's say if we see this as the epsilon vector, then sum of squares due to errors would be nothing but epsilon prime epsilon, and SS residuals would be nothing but E prime E. Okay, because if you do E prime E or epsilon prime, in this case let's say epsilon E prime E, then what will you have? You will have an E row vector and an E column vector. So E1 square plus E2 square plus E3 square plus En square. Okay, so that would essentially give you the sum of squares due to residuals, and then the criteria is exactly the same. We minimize the sum of squares of residuals in terms of the unknown variables, and then we land up at the estimate of beta, okay, which is nothing but x prime x inverse x prime y. Okay, this is a standard solution which you can memorize. Alright, beta hat is equal to x prime x inverse x prime y. So this will also be a, what would be the dimensions of this estimate? So x is how much? X was n cross p. So x prime would be p cross n, x would be n cross p, and this is a square matrix p cross p, so the inverse will also be p cross p, and then this would be a p cross n into n cross 1. So beta hat would be a p cross 1 vector. Okay, so the first element of beta 1 hat would give you beta naught. Okay, so beta was like this, no, beta naught, beta 1, beta 2, beta 3. So using this formula you would get beta hat, and then that would also be beta naught hat, beta 1 hat, beta 2 hat, and beta 3 hat. Okay, then you can just say estimate of beta naught is beta naught hat, estimate of beta 3 is beta 3 hat. Alright, and another thing that is very crucial that we learnt is that the decomposition of the total sum of squares. So in case of a multiple linear regression, what do we do? This remains the same. The total variation is divided orthogonally into SS due to regression, and this is SS due to residuals. Okay, so this degrees of freedom will be n minus 1 always. This degrees of freedom would be n minus p, and this would be p minus 1. Okay, so for a simple linear regression p equal to 2, and for a multiple linear regression p is greater than 2. Okay, this is the generalized form of the distribution of the split of the total variation into regression and residual sum of squares, and the uh, forms or distribution of the degrees of freedom of the respective sum of squares. All right, so any doubt if you have, please let me know. If not, we'll move on to the question sessions. Alright, I don't see any doubts, so I'll just proceed to solving a few problems which will help you in solving assignment 2 questions. Alright, so let us start with the first one. I hope you can see it. Okay, so the question is, a company manufactures refrigeration equipments as well as many replacement parts. In the past, one of the replacement parts has been produced periodically in lots of varying sizes. When a cost improvement program was undertaken, company officials wished to determine the optimal lot size for producing this part. One key input for the model to ascertain the optimal lot size was the relationship between lot size and labor hours required to produce the lot. To determine this relationship, data on lot size and work hours for 25 most recent production runs are utilized. Given that these things, consider fitting y equal to beta naught plus beta 1x plus epsilon to the data. A 90% confidence interval for beta naught would be how much? So, what do you think here is the response? So, which is the response and which is the uh, predictor? Can you ascertain that? Okay, so this question doesn't require uh, identifying what the predictor and the response would be, but I would just like you to think about it a little bit. Okay, so now we are given these figures and we have been asked to consider fitting the model y equal to beta naught plus beta 1x plus epsilon to the data. So what would a 90% confidence interval for beta naught look like? Okay, So first things first, we should have an estimate of beta naught hat. Okay, so in order to solve this, we should first find out beta naught hat, and beta naught hat is how much? It is nothing but y bar minus beta 1 hat x bar. Okay, so what is how should we find out beta 1 hat? Beta 1 hat is actually sxy by sxx, which means this is summation I equal to 1 to 25 xi minus x bar whole square into, sorry, not whole square, we wouldn't have these whole squares, I'm sorry. Okay, so x1 minus x bar yi minus y bar by summation xi minus x bar whole square. So this would be 70690 by 19800. How much does it come to? So this is something 3.57. Okay, so now that we have beta 1 hat, the next thing is to get estimate of beta naught hat. So this would be y bar, that is how much? Summation yi divided by n. So it would be 7807 divided by 25 minus 3.57 into x bar. X bar would be how much? 1750 by 25. So how much does beta naught come to? How much does this come to? So 7805 divided by 25 would, this is 312.2 minus 3.57 into 1750 divided by 25. This is 249.9. So it would be 312.2 minus 249.9. This is something around 62.9. Okay, so now we have an estimate of beta naught hat. Alright, now the next thing is to find out how beta naught hat is distributed. So yes, 62.38. Okay, fine, correct. Okay, 62.38 or 62.9, whatever is it. This is the value of beta naught hat. Alright, so first thing, we have calculated how beta naught hat is coming. The next thing that we have to do is that we have to find out or we already know, but we'll just brush up on the distribution of beta naught hat. So beta naught hat follows normal beta naught, and then this is sigma square, sigma square 1 by n plus x bar square by sxx. This is the distribution of beta naught. Now from here, if we transform the variable, okay, let's say we subtract and then write this like this: sigma square 1 by n plus x bar square by sxx. Then this variable, transformed variable, would follow a normal 0, 1. Okay, this is plain and simple transformation. For example, let's say if I have a variable x which follows normal mu sigma square, then x minus mu by sigma will follow normal 0, 1. This is a standard transformation rule. Alright, if you subtract with the mean and then divide by the standard deviation then of a normal distribution, then that transformed variable will also be a normal distribution with mean 0 and variance equal to 1. Alright, now we all know how a normal 0, 1 looks like. Okay, how does it look like? It is a symmetric curve, symmetric about 0. Alright, now here we will go a little backwards. Okay, so now we can say that this variable, since it follows a normal 0, 1 distribution, then if it lies between the let's say we want how much of confidence do we want? 90% confidence interval is the required limit. Okay, so now we can say that this distribution, since it follows a normal 0, 1 distribution, then if the value of the variable falls within these two blue lines that I am drawing, okay, and the blue line is such that the area above this is actually 0.05 and the area below which is the area is also 0.05. Okay, so I want to say this, that if this variable lies within this range, then the probability the probability of this variable to lie within this range would be 90%. Okay, because this total area is 90%. Alright, is this part clear to you? Any doubt, please ask me. If not, just give me a thumbs up or some indication so that I can proceed. Alright?
Clear.
Clear. Fine. Thank you. So here I have 90% confidence interval, so I want 90% confidence. So I can say, if I provide these limits, I will be sure that probability this lies between these two cutoffs, that probability is 90%. So exactly that thing I'm going to write. What I'll write? Probability. Now this actually is Z, if I write it as like this, Z 0.05, okay, this is also Z minus z 0.05. Z is the standard normal distribution. Okay, for a standard normal distribution, this point is actually 1.64. Okay, if it is not given to you, you can safely go ahead to assume that 1.64 is that number above which 5% of the area lies. Okay, so these two figures you can just memorize. Z 0.05 is 1.64 and Z 0.025 is 1.96. These are usually the standard values that we consider. You can cross check it with the table or from any other software also. Okay, so this one is 1.64. So I can write it like this, that probability minus 1.64 less than equal to 1.64, this probability is equal to 0.90. Okay, and here I am going to write my variable, which was beta naught hat minus beta naught by root over sigma square 1 by n plus x bar square by sxx. Okay, now sigma square here is actually unknown, but sigma square is estimated, as we have seen, by ms residuals. Okay, so instead of sigma square, I am going to write sigma square hat. Okay, anything other than beta naught in this context should be estimated. So sigma square hat would be ms residuals. Now how do I calculate ms residuals? Ms residuals would be sum of square ss residuals by, this is a one simple linear regression, so this would be n minus 2. Alright, this would be the df. So how do I calculate this ss residual? From here, so you remember this ANOVA table which I wrote earlier. SS residual is SST minus beta 1 hat SXY. Okay, so similarly we are going to write it here. So this is nothing but SST minus beta 1 hat SXY by n minus 2. Okay, so this is how much SST is SYY minus beta 1 hat SXY by n minus 2. So we'll put these values over here. 1 second. Alright, so if I put it here for reference, then how much do we get this as? SYY is how much? This is 307203. Okay, so this is nothing but oh no. So SYY is this thing, summation yi minus y bar whole square. So this is actually 307203 minus beta 1 hat. How much did we find out? Beta 1 hat was 3.57. So this is 3.57 into SXY. SXY was how much? It was 70690. 70690. This divided by n minus 2. N was how much? N was 25. So 25, sorry. So this would be 23. How much does this come to? Can you please calculate? So this would be 307203 minus 3.57 into 70690. This is something to be 54839.7 by 23. So this would amount to 2384.33. Okay, this would be 2384.33. all right, now we'll just proceed. We'll put this value of sigma square here and then we are going to proceed. But prior to that, let me just rearrange this thing. Okay, so now we have all the values that we need. Sigma square is estimated as ms residuals. We have the estimate of beta naught hat. We know what x bar is, sxx is, and everything is known apart from the true beta naught value, a true beta naught parameter. Okay, so now what we are going to do is that we are going to rearrange this equation over here so that we keep beta naught in the center. Ma'am, can you please mute your microphone? Alright, so what we are going to do here is that we are going to keep beta naught in the center and then rearrange. So how will we do that? We can write this same thing as probability minus 1.64 minus beta naught hat is less than equal to minus beta naught less than equal to 1.64 minus beta naught hat into, so first what should we do? First we should just take this and multiply so that we get something like this. So here what do we have? Minus 1.64 and here we have 1.64. okay, into square root of sigma square hat 1 by n plus x bar square by sxx. okay, this again multiply here also, sigma square hat 1 by n plus x bar square by sxx. okay, so then what do we have? Less than equal to, here we have beta naught hat minus beta naught. okay, and this entire probability is actually 0.9. alright, now if the focus is to keep the unknown parameter in the center. So if this has to be kept in the center, then we can write it as this has to be kept in center. So then we can write it as beta naught Okay, so if you consider these two equations, then beta naught would be less than equal to beta naught hat plus 1.64 into this thing. So this would be beta naught is less than equal to beta naught hat plus 1.64 into sigma square hat 1 by n plus x bar square by sxx. Okay, and if you consider these two equations, then beta naught will be, if we move it to the right hand side and these to the left hand side, then this should be less than or greater than or equal to beta naught hat minus 1.64 root over sigma square hat 1 by n plus x bar square by sxx. Okay, so then this probability is also 0.9. You understood? So then this is the lower bound and this is the upper bound, which is going to give me a 90% confidence that beta naught, the true beta naught intercept, lies between this and this. So I'll write it clearly once more. So then what we have, we land up at this thing, that probability beta naught hat minus 1.64 root over ms residual 1 by n plus x bar square by sxx is less than equal to beta naught less than equal to beta naught hat plus 1.64 root over ms residuals 1 by n plus x bar square by sxx. This probability is equal to 0.90. So therefore 90% confidence interval for beta naught is this value and this value. Okay, so this one, this entire thing will come over here and this entire thing will come over here. Okay, so why don't we just calculate this? Let us calculate from the numbers. Okay, so what do we have? We already have beta naught hat as we calculated it earlier. This is actually 62.38 or 62. What did I write? 62.38 or 39 something. Okay, whatever that value was. 62.38. So here we are going to write 62.38. MS residuals we calculated as how much? 2384.33. 2384.33. Okay, x bar is how much? X bar is 1750 by 25. So that would be 1750 divided by 25 is 70. So x bar is 70. Okay, and sxx is how much? Sxx is summation xi minus x bar whole square 19800. So this is 19800. So plugging these values, what do you get? All right, 1 second. I should tell you this. Okay, so this one 1.64 I have assumed when this followed a normal 0 1 distribution. But here, since sigma square is unknown, beta naught hat would follow a t distribution with degrees of freedom n minus 2. Okay, so this holds for a normal regression, but here whenever we are writing sigma square hat, so I should write it over here, but since sigma square is unknown, therefore beta naught hat minus beta naught by this thing, sigma square hat 1 by n plus x bar square by sxx, this will actually follow a t distribution, okay, a t distribution with degrees of freedom n minus 2. Alright, so then everything is going to remain same, but apart from these two are going to change, because for a t distribution with 23 degrees of freedom, these will not hold. So let me make this change over here. Okay, so this will be actually cutoffs of the t distribution. So here I would have something t 0.05 23, and this would be minus t 0.05 23. Okay, and then we have all the values. We have to plug in the values of these cutoffs and then find out what the actual value amounts to. So don't make this mistake like me, because sigma square is unknown, we are also estimating it. So then it becomes this beta naught follows a t distribution. Okay, so this would be minus 0.0523, and this would also be t 0.0523. Okay, so then we'll just find out the values and replace it over here. T 0.0523, how much does this come to? So we'll find it out from the tables. Let me just pull up one of the tables and we'll be able to discuss. Okay, can you see? Is the table visible to you?
Yes.
Okay, so now we want DF23, so we should focus on this row. What is happening? So we are going to focus on DF23. All right, now we want T 0.05. Okay, so what is that? That value will be this thing. Okay, area above is 0.05, area below is 0.95. So then the value is 1.714. Okay, so here we are going to write 1.714. Okay, this value is actually 1.714. and then accordingly this will also change. This will be 1.714. Okay, and here also this would be 1.714. So now if you calculate, what is the value that you get? You should get something close to 17.5 over here and something close to 107.2 over here. Okay, please check it whether you're getting it or not. Beta naught hat is 62.38 minus, first I'll calculate this square root term. Okay, so 1 by n plus x bar square by sxx is how much? 70 square divided by 19800 plus 1 by 25, okay, into ms residual, so 2384.33, and then square root of this. This is 26, so this entire term into 1.714 is actually 44.87. okay, so here we would have 62.38 minus 44.87, and this would be 62.38 plus 44.87. So this is coming to this is 107.25, and this one will be 62.38 minus 44.87. This would be 17 point something, 17.51. Alright, so then this is your required 90% confidence interval, 17.5, 107.2. okay, some decimal here and there might have gone, but the important thing to note here is if sigma square was known, then we would have proceeded with the cutoffs for the normal distribution. But since sigma square is unknown, we have to be very mindful of the distribution that we are considering. Okay, since sigma square is unknown, sigma square also has to be estimated, and this distribution in that context, when sigma square is estimated and not known beforehand, it follows a t n minus 2 distribution. Okay, so then the concept remains the same. This is also a symmetrical distribution, but this point is t 0.05 into n with df n minus 2, and this is minus t 0.05 n minus 2, such that this area is 5%, this area is also 5%. So we can say that we are 90% sure that this variable will lie within this region and this region, which happens to be 1.714. Okay, now be careful, this value will also change with the degrees of freedom, as we can see from this table. So for t distribution, always go to the table, and if the values are not provided to you, of course. And but if sigma square is known, which will most likely not be the case, then we can just proceed with the cutoffs for a normal distribution. That is all that I wanted to highlight. Okay, I did not plan on highlighting it, but I made a mistake in conveying the idea, so it's better that it got resolved. Okay, is there any questions now? Okay, so whenever, similarly, if you are asked to find out a 90% confidence interval, let's say the question is find out a 95% confidence interval for beta 1 from the same thing, then how would I do it? So normally beta 1 hat follows normal beta 1 sigma square by sxx. Okay, so beta 1 hat minus beta 1 root over sigma square by sxx, this would typically follow a normal 0 1, but here again the catch is sigma square is unknown. Okay, so we have to estimate sigma square. Once we estimate sigma square, then beta 1 hat minus beta 1 by sigma square hat by sxx, this then becomes, this again follows a t n minus 2 distribution. Okay, so if I have to find out a probability 95% confidence interval for beta 1, then I'm going to write it like this: probability this one, beta 1 hat minus beta 1 by root over sigma square hat by sxx. Okay, then this should follow, what should it follow? So this would be 95, so 0.95. So this should lie between t n minus 2 0.025. Okay, and this would be minus t n minus 2 0.025. Okay, then if we again rearrange, then what do we find? Beta 1 will be contained in, so 95% confidence interval for beta 1 would be then this thing, that t n minus 2 0.025 beta 1, sorry, it would be, if you rearrange, you would get something like this: beta 1 hat plus t 0.025 n minus 2 into root over sigma square hat by sxx, and this would be beta 1 hat minus t 0.025 n minus 2 root over sigma square hat by sxx. Now sigma square hat will be ms residuals, which we already have, sxx we already have, and now the thing that remains, beta 1 hat also we already have. The thing that remains is t 0.025 n minus 2. that we'll get from the table. Okay, so again 23, but this time 0.025, so we'll focus on this value. Okay, one tail will be 0.025, which means that this is the point above which 0.025 area lies, and cumulative probability is 0.975, which means below this the area is 0.975. So then that number then becomes 2.069. So here you have to go and plug in this value as 2.069 and then do all the calculations and get a 95% confidence interval for beta 1. Is it okay? Is it fine? Okay, clear? All right. Thank you. All right. So now let us move on to the next one. So this is the same thing actually. What they have asked? Consider the data in problem 1, 90% confidence interval on the mean work hours when the lot size is 65 units is how much? Okay, so mean work hours, if we have to find out, then that would be how much? That is y predicted. Okay, so this is beta naught hat plus beta 1 hat into x naught. Okay, here x naught is how much? This is 65. So then y hat will be how much? Given x naught is equal to x naught, this would be beta naught hat. So it would be 62.38 plus 3.57 into 65. How much does it come to? So this will be ma'am, if you could mute your system, it would be really good. So this is 294.43. So this would be 294.43. Alright. Now what is being asked? Mean work hours when lot size x is 65 units. So from here also it's clear that lot size is the predictor and work hours is the output. Fine. Now we have to find a confidence interval for predicted for mean work hours when lot size is x equal to 65 units. So essentially what we need is we have to find out this expectation of y given x equal to x naught and the confidence interval for this one. Okay, so this thing we have found out, expectation of y given x equal to x naught. So this thing we have found out. Okay, now what is or how does a 90% confidence interval look like? It looks like this. Expectation of, sorry, this looks like this. Expectation of y given x equal to x naught hat plus minus root over ms residuals into 1 by n plus x naught minus x bar whole square by sxx, and here we are going to add that term t n minus 2, and what is our confidence? 90% confidence, so it will be 0.05. Okay, so then we'll just substitute and then find out what the answer is. So this would be, how much it would be? It would be 294.43 plus minus 1.714 into root over ms residual was how much? 2384.33, 1 by 25 plus 65 minus 70 whole square by 19800. Okay, so whatever comes, that will be the confidence interval. So most likely the confidence interval would be 277.4 to 311.4. Okay, check. Any doubt? No? Alright, this question says that if 100 into 1 minus alpha confidence interval for beta contains 0, then what should we do? Should we reject h naught beta equal to 0 at alpha level, or should we accept h naught beta equal to 0 in alpha level? So what do you think we should do? If this, let's say 95% confidence interval beta is containing 0, it means that we are 90% confident that 0 will lie within these bounds. So if 0 is lying within this bound, then we will accept this, that h naught beta equal to 0. Is it okay? Is it understandable why will we accept this? Because we are 100 into 1 minus alpha percent sure that 0 will lie within these ranges. So it means that beta, the true beta is very very close to 0, right? So if the confidence interval contains beta equal to 0, then we are going to accept the null at alpha level of significance. All right, moving on. Suppose this one, if we consider a simple linear regression model where intercept beta naught is known Okay, then what is the least square estimate of beta 1 for this model? So let's say if beta naught is known, then we can always write, so then the unknown parameter that we have here is the beta 1. So then we'll have sum of squares, or residual sum of squares will be summation yi minus beta naught minus beta 1 x whole square. And since beta naught is known, it's no longer a parameter, we will have to just differentiate in terms of beta 1. So d beta 1 ss residual would be how much? It would be summation 2 yi minus beta naught minus beta 1 x into minus x, and then what do we have to do? We have to equate it to 0. Alright, and then we'll have to solve for beta 1 hat and see how much beta 1 hat amounts to. Is it okay? So if we solve for this, then how much do we have? This is actually summation yi minus beta naught into xi minus beta 1 summation xi square equal to 0. So then we'll have beta 1 hat as summation yi minus beta naught xi divided by summation xi square. Okay, since beta naught is known, we do not differentiate with respect to beta naught. Is this okay? Alright, now we'll move on to the next one. So consider the model in problem 4, same thing. Then what is the expectation of beta 1? It would be expectation of beta 1 hat. Okay, so then beta 1 hat is how much? This is actually summation yi minus beta naught xi by summation xi square. So expectation of beta 1 hat would be expectation of this entire thing. Since this is not random, we'll have 1 by summation xi square. Okay, and here we'll have summation expectation of xi is not random, so we would have yi minus beta naught into xi. Okay, now yi is how much? Yi is beta naught plus beta 1 xi plus epsilon. So expectation of yi is how much? Beta naught plus beta 1 xi. Okay, so then this one we can write it as summation beta naught plus beta 1 xi minus beta naught into xi by summation xi square. So this beta naught cancels out, and we are left with beta 1 summation xi square by summation xi square. This will also cancel out. So then expectation of beta 1 hat is actually beta 1. Okay. Is it clear? Alright. and then we come to the same thing, variance of beta 1. So variance of beta 1, again it will be hat over here. That how will we calculate? Same thing. Here we have 1 by I'll write beta 1 hat once more. This will be summation yi minus beta naught xi by summation xi square. Okay. Now variance of ax is actually a square into variance of x. Okay. Please remember this thing. So now if variance of beta 1 hat we have to calculate, then we have to write it like this, that 1 by summation xi square whole square, because this is non-random, this comes out. Then what do we have? This, the yi's are independent. Okay, this is something we should keep in mind. So we'll have summation, again here xi square, variance of ax minus b, where b is a scalar, is actually variance of ax. So here beta naught is actually doesn't matter, so we'll write here variance of yi. Okay, so then this one cancels, so we are left with sigma square by summation xi square. Okay, so this is the variance of beta 1 square. Is it clear? 1 by xi square whole square comes out. Then variance of summation equal to summation of variance. Variance of summation x equal to summation of variance x if xi's are independent. Okay, which is true for this case. Okay, and because here the assumption is that the n individual elements do not depend upon each other. So then we can write this variance of summation, we'll take summation in summation out and variance in. Then we have xi into this y term. Xi is again a scalar, so we'll take out the square of it, xi square, and then we have variance of yi minus beta naught. Now beta naught is a scalar, so we'll ignore it, we'll write variance of yi. Fine, is it okay? Alright, so moving on, this is probably the last question for today. What does the adjusted R square value tell you in a simple linear regression model? So this tells how much of the variance in response can be accounted for by the regressor variable. So then the understanding is that if we keep on adding predictors, so in multiple linear regression what do? We keep on increasing the predictor. Okay, so predictor plus 1 or something. Instead of 1, in case of simple linear regression, we'll have two regressors or three predictors or 4 predictors. Now as we keep on increasing the number of predictors, our prediction becomes R square value increases. But then how much can it increase and how much can it decrease? Okay, that value will be given by adjusted R square. Okay, so what happens is that if we keep on adding variables, R square value will increase, okay, as number of predictors increase. But adjusted R square will not show that relationship. Okay, it might increase to a certain extent and then it might fall also. Okay, so adjusted R square will give you the optimal number of predictors to include in your regression model. Okay, is it clear? All right, then the last question, maybe this is also a small thing. So what happens if we fit something like this, y equal to beta naught plus epsilon, no predictor? Then r square will be 0, because r square is that amount of variation that is captured by the predictors. So if there are no predictors, then r square value will be 0. Is it okay?
Yes.
All right, so I think we have come to the end of today's session. If any doubt exists, please let me know, and I'm going to clear it in the next class. You can also post it in the discussion forum if you like to, and then we'll start off with where we got stuck in this class today. All right, so the key idea is to get the point estimates, use them to get the confidence intervals, get the appropriate distribution with the appropriate DF, find the cutoffs, and then decide upon whether to accept or reject the null hypothesis. So if the true value h naught beta equal to whatever, if it falls within the confidence region, then we are going to accept h naught. Okay, and these two are equivalent, falling within the confidence region and falling beyond the cutoffs. Okay, so if it is beyond the cutoffs, it will not fall in the confidence region, the rearranged thing, so we are going to reject. But if it falls within the confidence interval, we are going to accept. All right, if not anything, then thank you so much for joining, and I'll see you in the next class.
Okay, thank you.
Thank you.